Good afternoon, everybody.
Good afternoon, Professor.
All right, I have a few announcements, same as on Monday. Your midterm number 2 will be this coming Monday, November 15, from 4 to 5 p.m. on iLearn. Same format, multiple choice, ordering questions, multiple answer, and true or false, between 25 and 30 questions. It will cover lectures 10 to 17 and homework 4 through 6. Because of Veterans Day, the campus is going to be closed tomorrow, Thursday. So people who go to discussion sections on Thursday will not have a discussion section. So I believe your TAs have notified you already. If you would like to meet with me, I'm not going to have office hours unless you let me know that you want to meet with me. So if you send me an email and I know that you're coming, I will have my regular office hours from 2 to 3. We can go over the homework if you'd like, since the people on Thursday are not going to have a chance to go over it with your TAs. So you're welcome to do that. And I think that's it. So enjoy your day tomorrow. And for today, we will continue to talk about black holes. So last time we introduced black holes as being objects where gravity is so strong that the escape velocity of the object becomes extraordinarily fast, extraordinarily large. And so it reaches the speed of light, or greater than the speed of light. And since nothing can go faster than light, then that means that nothing can escape a black hole. And how they form, at least one of the ways in which they form, is at the very end of the life of a high mass star after it explodes as a supernova and the core collapses and nothing can oppose the force of gravity that is collapsing it, because electron degeneracy pressure fails, neutron degeneracy pressure also fails, and then we don't know of any other type of pressure that would be able to stop the collapse. So they collapse to an infinitely small object with a gigantic amount of gravity, right? So surrounding this infinitely dense and infinitely small mass, which we call the singularity, is the event horizon. And we talked about the event horizon last time as being the distance between the singularity and the place where the escape velocity is equal to the speed of light. So we can ask, how big is that event horizon? Does it depend on, is it the same for all black holes or is it different? So it turns out that it is different, because you can imagine how so think about the event horizon as being the boundary, right? The surface or the sphere around the black hole, where if you cross it, you can never escape again. If you are like in this figure, if you're just a little bit outside of the event horizon, you could potentially have enough speed to get away from the black hole. But once you cross that boundary, the event horizon, you cannot do it, because you would have to be going faster than the speed of light in order to get away from the black hole. And that can't happen. In the universe, as we know it, nothing can go faster than the speed of light. So you can imagine how if a black hole has more mass, you would have to be farther away from the singularity in order to get away. If the black hole has less mass, then you can get a little closer. So this thing, the event horizon, will scale with mass. So we call that the distance from the singularity to the event horizon. We call that the Schwarzschild radius. This is named after the German scientist who figured it out, right? So Schwarzschild. And so the Schwarzschild radius is just the distance from the singularity to the event horizon. And you can calculate it quite easily if you know the mass of the black hole. Right, so I'm getting a couple of questions about, and actually I had a question last time asking me about, is it true that the universe can expand faster than the speed of light? And the answer is yes, because it's not something that is moving, right? It is an expansion, and that actually can happen. But that's, we will talk about that in many lectures, right? Toward the very end of the quarter. And thinking about, does gravity move faster than the speed of light? And it is, can you think about, again, gravity doesn't really move, but what moves or what travels is the information. And the information of gravity does take a while to travel. And we'll actually talk about gravitational waves, which is the effects of gravity on space. And we'll talk about that at the beginning of next lecture. So we'll get to those questions. But let me just tell you how to calculate this Schwarzschild radius. So the Schwarzschild radius of the event horizon can be calculated with very simple math, right? It's just an algebraic equation, which you do not need to remember. But sometimes I get comments in this class, since I do have quite a few students from CNAS, they get frustrated because like, there's no equations. Okay, here you go. Here's one of them. How do you get that? How do you figure out what that distance is? Well, it's very easy. You go from the equation for escape velocity, which I gave you last time. It is a manipulation of the equation of gravity, basically. So you get the velocity, the speed with which an object would have to go in order to completely escape a gravitational field, which is equal to 2 times the gravitational constant times the mass of the object that you're trying to escape, divided by the radius of the object that you're trying to escape, right? So we know that. And all you would have to do to get the radius of the event horizon is substitute that velocity for the speed of light, which is c. So you substitute it for c, so that tells you the radius at which the escape velocity would be equal to the speed of light. And so you do a little bit of algebra, right? Square both sides and then solve for r, and that's what gives you the Schwarzschild radius. So that's, again, for people who complain about not having equations. For everyone else, the distance from the singularity to the event horizon, black hole, in specific unit. It has to be in solar masses. Oh no, I'm freezing again. Okay. Thank you for letting me know. Okay. Let me see. I think I'm okay. All right, let me know if I start freezing again, and I'll try to change to another network. So again, if you know the mass of a black hole, which I will tell you how to calculate it, but that'll be next. So if you know the mass of a black hole in solar masses, then all you have to do is multiply that number times the number 3. And that will give you the radius of the event horizon, the Schwarzschild radius, in kilometers, right? A kilometer is about 0.6 miles. So if you know the mass of a black hole, and you know, if you know the mass, that's all you need to know, then you just multiply it times 3, and that gives you the radius in kilometers. That's the part that I want you to remember. So remember this, remember that if you have the mass of a black hole in solar masses, you just multiply it times 3, and that gives you the radius of the event horizon in kilometers. So remember this, not this. You don't have to remember that. All right, so then let me do a couple of polls for this. So no, not this, hold on. Sorry about that, so polls, here we go. All right, so it's 2 questions. Here we go. So the first question, the event horizon of a 3 solar mass black hole, right? Like a black hole that has a mass of 3 solar masses, has a radius of, you have four choices: A, 1 kilometer, B, 3 kilometers, C, 9 kilometers, D, 3,000 kilometers. And the next question in the poll is our galaxy, as we will see, has a supermassive black hole in its center with a mass of about 4 million solar masses. So 4 million times the mass of the sun. So how big is the radius of its event horizon? A, 9 kilometers, B, 4 million kilometers, C, 12 million kilometers, D, 150 million kilometers. All right. Okay, while I answer, let me see. So I have a couple of questions that I'll get to while you're answering that. Well, just how do you measure a black hole's mass? Okay, that'll be the next thing we talk about. So, and does a black hole appear black because there is no light escaping from it? Yes, that's correct. You can't see any images coming out of a black hole. So that's why it looks like this black thing. That's where the name comes from, right? Black, it's like, looks like a hole. All right, so let me end the poll and share the results. And okay, so this was a simple thing, and the answers that most people got are correct. All you have to do is multiply the event horizon of a 3 solar mass. How do you know the radius of the event horizon? It's 3 solar masses times 3. That gives you 9 kilometers. So answer C is the correct one. For the next one, our galaxy has a supermassive black hole of 4 million solar masses times 3. That would be 12 million kilometers. So that's answer C again. All right, so this is simple. Part of what I wanted to do is show you how small, relatively speaking, the event horizon of a black hole is. So for example, for the first one that we talked about, 3 solar mass black hole, that's about the smallest black hole that you can form after a supernova. So for a small black hole, right, relatively speaking, it's only 9 kilometers. That's pretty small. I mean, you can get very close to that black hole and still have a chance of escaping. Whereas even a black hole that is as huge, as massive as the one in the center of our galaxy, I mean, 4 million times the mass of the sun, that's crazy, right? Okay, 12 million kilometers, that sounds like a lot. But when you consider the scales, I mean, the distance between Earth and sun is 150 million kilometers. And that's just our little solar system, right? And compared to that, 12 million kilometers is really not all that much. If we had a super massive black hole in the center of our solar system, we wouldn't be inside of the event horizon. Venus wouldn't be inside of the event horizon. And I think Mercury wouldn't either, although I don't remember off the top of my head what the distance is. All right. So here's a summary that's just for your notes of black hole, singularity, event horizon, and Schwarzschild radius. All right. Now, you probably have come across a picture that looks like this. And if you do a quick Google on black hole, you'll get a lot of different things, but this will be one of the pictures that you get. And so I'm going to spend the next few minutes explaining why. Why do we draw black holes like this when really they're kind of like a sphere? All right, so what happens is that this picture refers to Einstein's theory of general relativity. One of the things that Einstein is the most famous for, and that is such a useful theory, right? Because we explain so many things in the universe thanks to this theory. What Einstein envisioned in his theory of general relativity was gravity not so much being a force that pulls things together, but being something that makes mass curve space-time. And we talked about, space-time last time. So we talked about how there are 3 dimensions of space and then 1 dimension of time, so 4 dimensions altogether, and we call that space-time. So when you so imagine the entire universe being this fabric, this thing in 4 dimensions, which we do not know how to draw 4 dimensions, right? I know some of you may be art majors and you might have talked about this, like how do you draw 4 dimensions? And I know some mathematicians, I think we have at least one in class, who might also think about how to represent 4 dimensions. For the most part, we don't know how to do that, right? We don't know how to draw. So instead, we sort of collapse them all into 2 dimensions, like into, like a sheet. This always happens here. Well, I was trying to show you a sheet. So something in 2 dimensions. And then we say, well, this 2-dimensional thing represents the 4 dimensions. And so that's what you see here as being this, this lattice. And so when there is a mass, it curves it. It causes it to bend. And that's how Einstein envisioned general relativity. So any kind of mass, like in this case, it's the sun or a star with a planet going around it, is because of the curvature of space-time. So in this idea, gravity is caused by, oh, did I freeze again? No, okay. Gravity is caused by the curvature of space-time. So a massive object curves the space-time around it. But if you're far away from the object, then space-time is nearly flat, right? Because there's no mass around it, so it doesn't get bent. But if you go closer to the object, then the curvature will form a dip or a well. So in Einstein's picture of gravity, other objects, right? You have one object that is causing the curvature, any other object that is around it will sense that curvature and they will be drawn into the well. The thing that you might be familiar with, right, and here's again from my kiddos in Malawi. So when you have like a funnel that has a curvature and you put marbles going down them, so they will follow an orbit that goes around and around and around, right? Because of friction, they will lose energy and eventually here on Earth, like it'll eventually go down. But if there was no friction, they would just keep going in the same orbit and they would go around and around and around. And that's what we have here again in space, where there is no friction and things don't lose energy and they can just keep going around and around. So this is Einstein's idea of general relativity. And I have a video that I like a lot that illustrates this and later on black holes. So let me show that to you. Let me go here. So
the current idea of this bizarre creature comes from a radical view of space, time, and gravity.
Universe according to Albert Einstein. Albert Einstein had this crazy idea that space and time will...
Sorry, it always does this. It stops when I make it into a full screen, it stops. So let me try it again.
To Albert Einstein.
Albert Einstein had this crazy idea that space and time were curved, and it was the curvature of space that gave the appearance of gravity.
We tend to think of space as rigid and stable, but Einstein proposed that space and time are woven together in a flexible fabric. Massive objects like the sun actually bend and warp the fabric of space-time, creating troughs that smaller objects can fall into.
What actually happens is matter warps space-time. So the very space, the three-dimensional space that we walk through, warps slightly. Every time when I walk through space, space around me warps in on me ever so slightly, but because we're not very massive, it's so minuscule that we don't sense it.
If an object is massive enough, like the Earth, it will warp space-time so we can sense it and fall towards it. That's gravity. But what happens if an object is much, much more massive than the Earth or the Sun? In theory, it could warp the fabric so much it would create an actual hole in space-time. Once something fell in, it couldn't escape, not even light itself.
So imagine a place where the gravity is so strong, turning on a flashlight. The light would go up and it would never leave. It would curve and come back down just the way a tossed ball on Earth. It's not traveling fast enough, it goes up, curves, and comes back down.
Space itself is falling inside the black hole. It's rather like a river falling over a waterfall. It's like that, except it's space itself that's falling over the cliff. There's a place where the space starts moving faster than light. So the light, which is trying to get out, it's rather like a kayaker trying to make their way upstream on a river that's going too fast. They get dragged down to the center of the black hole.
Gravity becomes a riptide. The closer you get, the stronger the current. Eventually, you reach the event horizon, the point of no return. Deep inside, whatever goes in is lost in a point of infinite density.
The matter goes inside the surface of the black hole, shrinks down to the very center, where it gets destroyed in a region of infinite warped space and time, and it's gone.
And so, it seems, are the laws of physics. At the center of a black hole, all equations break down. Even for physicists, what happens deep inside a black hole is a mystery.
We're in want of a new idea about how to explain what matter does at the center of a black hole. We're in need of a new law of physics.
Einstein himself concluded black holes were too strange to be real.
Albert never really liked the idea of black holes. He thought they were anathema. This was something that nature should avoid. The places where space and time became infinitely twisted up, he thought, no, nature shouldn't allow that.
Black holes are certainly odd beasts in the universe. They were thought to be peculiar, so peculiar as to perhaps not even really exist in the real world. Simply because your equations show that they can exist doesn't require that the real universe has them.
But over the years, suspicions rose. Stars were found behaving strangely, orbiting invisible objects, moving faster than expected.
Even though a black
All right. All right, so I'm getting a lot of really interesting questions, and some of them I believe were answered by the video, so hopefully you got the answer. I am going to resist the temptation of talking about them because I know myself, I'll just go blah, 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 and we won't get to what we need to cover. I'll be happy to answer them at the end of class. And some of the questions you guys asked, some of the ones you asked will be answered in the next few slides and also by the video. So anyway, so back to this picture, right? In our solar system, the sun is the biggest mass, so it's causing the biggest curvature. And again, be careful to remember that this is not the actual picture, because space has 3 dimensions of space and 1 of time. So it doesn't exactly look like this. This is just so that it can fit in our brains, right? So that we can visualize it. But it's entire space that is curved. And I like this video because there is one part where they do the curvature in 3D, and that looks a lot better. And that's not even taking into account time. So anyways, like the video said, when you get a black hole, what happens is you get the mass more and more and more concentrated. It's not just that it's more mass, it is the fact that it's more concentrated. So if you think of a rubber sheet that is stretched and you put a big beach ball, for example, you know, it's a big ball and it's not going to cause much of an indentation. But if you put, I don't know, something like a small steel, a small ball that is made of steel or iron or something really heavy, and you put it in on the sheet, then it's going to get very bent. The idea of a black hole is that it's one where it basically forms a bottomless pit on this fabric of space-time. And it strongly warps space and time in the vicinity of the black hole. The event horizon. The event horizon would be that point where, like in the video, if you're trying to kayak and it just becomes basically vertical and it doesn't matter how fast you try to kayak, you're not able to get out of it. So that would be the event horizon in this 2D representation of the black hole. So that's why, I hope I answered the question. Why do we represent black holes like this? It's just talking about Einstein's theory of general relativity, showing how a black hole bends space in an extreme way. It warps it and it creates some sort of a hole, right? A bottomless hole. So for the next 20 minutes, I am going to talk about observations of black holes, and that will answer a couple of the questions that you guys asked during the video. So do they really exist? Have we seen them? How can we detect them? So, and I'll tell you how in general, and then I'll tell you about 3 major recent discoveries that have made the news in the last few years. And we'll cover hopefully 2 today, and we'll cover the 3rd one next time. So, all right, so how do you look for black holes, right? As some of you pointed out in the chat, we cannot see black holes. In fact, they would look like black, like a black sphere, because light cannot come out of them. So therefore we cannot see them. The problem is when you put a black sphere that is fairly small against the black backdrop of the universe, it becomes really hard to see them. So you can't see them directly. But just like the wind, right? You cannot see the wind, but you can see the leaves when they're being blown by the wind. You can see branches, you can see trees. So you know the effects of wind. You know that there's wind because you can see the effects of it. In the same way, you cannot see black holes, but you can see their gravitational effects. So basically, you can see the things that are being attracted by black holes. And they're easiest to find in 2 specific cases. So you can see them if they are enclosed binary stars. And by binary stars, I just mean 2 stars that are going around each other. So imagine that you had 2, well, I'll get to that in the next slide. So those are called stellar mass black holes. And the second way or place where they're easier to find is when they are in centers of galaxies. And those tend to be what I alluded to before, the supermassive black holes. All right, so stellar mass black holes. These are the ones that result after a star goes supernova, and the core contains more than 3 solar masses. So, and that's what we call stellar mass black holes, because they have the mass of about a star. So they're the small ones, right? For those of us who study this in astronomy, these are the small type of black holes. Their masses range between 3, which would be the smallest, to 10, 20, we're not sure. how many, but more than 10 solar masses. So far, astronomers have found more than 20 candidates. And this is one of those things that Wikipedia is pretty good for, because you go to the black hole page and it'll give you a list of all of the candidates that have been found. How do they form? First of all, supernova, as I mentioned. But they can form in other ways. And I discussed this with a few of you who stayed at the end of last lecture. You can have, for example, white dwarfs, neutron stars or white dwarfs that accrete mass. So somehow they manage to attract mass from other stars or a nebula, and it goes into the neutron star or white dwarf. And if it's more than 3 solar masses, then again, there's no degeneracy pressure that will work against that, and it'll collapse to a black hole. So that's another way that they can form. Or this is kind of this is a cool one, because it's one that astronomers only discover relatively recently, and it is when you have 2 neutron stars that are going around each other and they start spiraling in and then they merge. But neutron stars have more than 1.4 solar masses. So if you get 2 of those, very likely you're going to end up with an object that is more than 3 solar masses. And again, it's going to become a black hole. So these are some of the ways in which they can form. So how do you detect them? So basically, as I was saying before, as I started saying before, you can have a binary star where you have 2 stars that are born more or less at the same time, and they end up being trapped by their gravitational fields, by their gravitational attraction, and they end up going around each other for their entire lives. So what happens if one of them is a lot more massive than the other one? The one that is more massive is going to go supernova first, and the core will become a black hole. And then let's say that the other one continues its life, and then eventually the other one becomes a red giant. So that's what this picture is showing here. The other star becomes a red giant. When a red giant forms, or when a star turns into a red giant, as you know, it becomes much, much bigger than it was before. So that means that the edge of this companion star, companion to the black hole, is going to get a lot closer to the black hole. At that point, some of the material, and I had it here too, some of the material will start falling or circling around the black hole. So when that happens, so if the visible star is close enough to the black hole, the outer layers can be attracted to the black hole. And because of conservation of angular momentum, they start to spiral down to the black hole and they form a disk. This should sound like a familiar story, right? Like pretty much anything that is rotating in the universe ends up forming a disk at some point. Because that material is going so fast, it gets very hot. There's a lot of friction, right? So and when you have friction, things get hot. And it gets so hot that it can emit X-rays. And those X-rays can be detected. So when you see a star that is going around something, but you don't see the companion, it's invisible. And that companion, even though you can't see it, there's something around that companion that is emitting X-rays. What you do is you have to go and try to measure the mass of the black hole. Oh, sorry, the mass of the thing that you cannot see, right? Of the invisible companion. If it is more than 3 solar masses, then it has to be a black hole. If it is less than 3 solar masses, it could be a neutron star. Neutron stars are very difficult to see. So it could be that it's just a neutron star that also has an accretion disk and that is emitting X-rays. Now, to your question, how do you measure the mass? You basically have to use actually very simple math. right? So if some of you learned about Kepler's laws when you were in high school, and Kepler was an astronomer a long time ago who figured out certain things, certain laws that you may have learned. One of them was that if you could figure out the period, so how long it takes for a planet to go around the sun, and if you know the distance between the sun and the planet, doing very simple math, and this was empirically, I mean, he figured out empirically, doing very simple math, you can figure out the mass of the planet, or the mass of this, the mass of the sun and the planet together. So Newton came after Kepler, and Newton came up with the law of gravitation, right? The force of gravity and the equation for the force of gravity. So Newton applied his equation of gravity to Kepler's observation that if you can figure out the period, you know, or in other words, how fast an object is going around another object, and you know, if you know the distance between them, then you can figure out the sum of the masses. And if you're more interested in the mathematical details of this, I refer you to your textbook. It gives you the equations and shows you. But the bottom line is that all you need to know is how fast the star is going around, how far away they are from each other, and that will give you the mass of the objects. So if you can figure out the mass of one, then you'll know the mass of the other. And this is the game that we play to figure out the mass of black holes. Very long explanation that will not be on the test, but that's how we do it. So here is an example of the very first black hole that was discovered. The name of this black hole is Cygnus X1. Cygnus because it happens to be in the constellation of Cygnus, which you can see in the summer. X1 because it emits X-rays, and it was the first one that they found in the constellation of Cygnus that had X-rays. So this black hole was discovered, let me see the exact year, I have it in my notes, 1964. Einstein predicted, like the video said, Einstein predicted that there were black holes back in 1916, right? So it took almost 50 years before they actually found the very first candidate for black hole. So in 64, which of course you don't have to remember, in 1964, this X-ray source was discovered. So what you see here with the arrow, that's the star that you can see. The black hole you cannot see because the black hole is very small, it's invisible, it has an accretion disk around it. But what you do see is this big star that is going around something that you cannot see. So people got very excited, right? Because this may be the proof that Einstein was right, even though Einstein didn't like it, right? Einstein himself thought, well, that's just my math, but it doesn't really mean they have to exist. And so, yeah, so it actually took a long time from 1964 until the time when it was established that it actually was a black hole. So, yeah, one thing that I wanted to mention, Cygnus X1 is a special object to me because that was actually, let me see, that was actually the very first scientific paper that I wrote, that I published. So this is when I finished college. I took a year off and I went back to Mexico and I worked there at the university for a year. And my supervisor was working on X-ray binaries, Gloria Königsberger. And so I worked with her and we went to San Pedro Martir in Baja and we made some observations, and I actually got to write this paper. That was my very first one, where we did an analysis of the big massive star. So anyways, that's where my roots are on black holes. Anyways, interesting thing about this black hole, most of you are familiar with Stephen Hawking. And Kip Thorne, who was in the last video, he's a physicist at Caltech, and we'll talk a little more about him later. Apparently, when Cygnus X1 was discovered, Stephen Hawking didn't believe it. He didn't believe it was a black hole. And so Kip Thorne thought, yes, it is a black hole, and they made a bet. And back in 1964, and Stephen Hawking was very keen on saying that it wasn't a black hole. They made a bet, and finally in 1990, there was so much evidence showing that it was a black hole that Stephen Hawking had to concede. And I think the bet was a subscription to a magazine or something, so Stephen Hawking had to pay for it. Anyways, so that's about that one. All right, besides stellar mass black holes, we have a different type of black holes, which is what I actually study for a living, which are supermassive black holes. These are way bigger, and they cannot possibly form from just the death of one star or even the merger of a couple of stars, right? Or a couple of neutron stars. They have masses that are between 1 million black holes and 1 billion. Sorry, I got distracted with a question. Supermassive black holes have masses that are between 1 million times the mass of the sun and 1 billion times the mass of the sun. Or in fact, the biggest one that we've ever observed is 10 billion times the mass of the sun, which is ginormous, right? It is like 1/10 of the mass of the entire Milky Way, our entire galaxy. These live in the centers of galaxies. And our Milky Way, the galaxy where we live, has a supermassive black hole in its center. And that's the first discovery that I'm going to talk about in the next few slides. And I think that that'll be all we have time to cover. Most other galaxies also have supermassive black holes in their centers. And this has been actually one of the biggest discoveries in my career, because when I started working on black holes, we didn't know they were so common. We thought that only some galaxies had supermassive black holes in their centers. But in the last, in my entire career, in the last 20 years, we have discovered that pretty much every galaxy has a supermassive black hole in its center. How do we detect them? Well, very similar to the little ones. We can't see them, but we can see the motions of material as they go around the supermassive black holes. And that leads me to the first discovery that I will talk about. And by the way, I'm getting a lot of questions and I love them and I get so distracted by that. But just to answer the question that I think it's some of you are asking, and if not, you will, how do they form? Well, this is one of the things that keeps me employed. We still don't know. We don't know how supermassive black holes form. There are about 4 or 5 theories of how they form. 2 of them, the most promising ones, which I will tell you after we finish class. But the bottom line is we don't know. And I have an NSF grant actually right now that is specifically to investigate how they form. But there's not just me, there are a lot of astronomers working on this, and we still don't know. That's the bottom line. Let me get through this. Just to clarify, a galaxy, we'll talk a lot about galaxies next week, but a galaxy in general is a collection of stars that are held together by gravity. So this is an example of a galaxy. This is the Andromeda galaxy that is close to us. And each of these galaxies seem to have a supermassive black hole in the center. And again, we don't know why yet, but we will. All right, so here's the first discovery that I wanted to talk about. For many decades now, a group of people from UCLA, Andrea Getz, and a whole team, and Reinhard Genzel, who is actually now at UC Berkeley. So UC Berkeley and UCLA people have been looking at the motions of stars that are very close to the center of our galaxy. They needed some technology that took a long time to develop in order to be able to see individual stars that are very far away from us, right? Like thousands of light years away from us. And so what they saw was that, let me play this again. This is a movie that was performed with years and years and years of data. So starting in the 90s, you can see the stars that are going, the plus here marks the center of our galaxy. You don't see anything in there, but you see how the stars move, and particularly this one, which they call S2, as it gets close to the invisible center, it speeds up, right? Kind of like comets do when they go around the sun, or it's like a slingshot. And when do stars do that? Well, when they get close to a massive object like the sun, right? But in this case, they're going incredibly fast. They're actually going at a fraction of the speed of light. And so by using, again, Kepler's third law with Newton's math, they were able to figure out the mass of this invisible thing. And the mass turned out to be more than 3 million times the mass of the sun, or 3 million solar masses, between 3 and 4 million solar masses. So this was an incredible discovery, because a lot of people have remained skeptical about whether black holes exist or not. And this was the thing that made everyone be like, there is no way you could have that much mass in that small amount of space that could be anything but a black hole. So this was the discovery that convinced pretty much everyone. I don't know of any skeptics anymore about whether black holes exist or not. And I'm talking about scientists, right? I mean, so of course, because it was a major discovery, this led to a Nobel Prize last year. So in 2020, the Nobel Prize of Physics was given to Professor Andrea Getz at UCLA and Professor Reinhard Genzel at UC Berkeley. So they're all part of the family, right, of our UC family. And it was for showing that there is a black hole at the center of our galaxy. Okay, so in the last minute, I will just say that the only galaxy where we can look at individual stars is our own galaxy. Other galaxies are too far away. So we have to play a slightly different game, which is we have to not observe individual stars, but observe groups of stars or gas that emits some light. And so we look at their orbits around the black hole. We measure their velocities with Doppler shift, which we talked about before. And then in that way, we can calculate the mass of the black holes. And as I said before, this has shown that the majority of galaxies have supermassive black holes at their centers. All right, so it is 4:50. I will stop here, and I have a lot of questions to go to. So I will answer those, and the rest of you, I will see you on Friday.
Thank you, Professor.